Acum se aude? Da, se aude cum aud și eu.
Trebuia ceva apply, probabil, dat.
Ok.
Na, bine. Nu, probabil că nu dădusem apply, cine știe ce.
Opriți microfonul până când nu începem.
Da.
Good morning. Good morning. Hello. Hello.
Hello, finally I can see you.
Oh, terrific. I can hear you now. Okay,
Hi.
perfect. Good. Hi, how are you?
Both us are
Can
here.
you-
We can see each other.
Oh, yeah, terrific. Can you see my screen?
Now I'm
you-
seeing you now.
Oh, okay, but not my screen, right? Hi, how
No,
are
no,
you?
no,
How you doing?
hi. No, not
Good.
yet.
Not yet. Yeah, because I pressed the screen share and it's supposed to, it was supposed to say share.
Yes.
Let's see later. layout.
We can see the screen, but before probably.
And presentation. Okay, let's see, menu.
Da? I think Dariana is seeing your screen.
Oh, you can see my screen?
Yes, I can see your screen, but I don't see the presentation.
Oh, okay. Here's the
Now,
presentation.
okay,
Can
now
you,
it's the presentation. Okay, we managed to see it.
No.
you can see it?
Okay. Yes, we can see.
Oh, perfect. So this is the presentation. Perfect. Good.
Okay.
So it's working. That's great.
Awesome.
That was it. Well, thank you so much for having me, and I'll see you guys in the future again.
Yes.
Short and sweet.
Yeah, that was short. Yeah.
We have face to face, not only online, because we already have so many video conferences. So
I know, this is so crazy.
too much.
This is like a crazy time.
Exactly.
Yeah.
So let's see. Maybe we are waiting
For a couple of more
minutes.
Yeah. No problem.
Yes.
Take your time. Yeah.
5 minutes or something, not more.
Sure. Yeah. No
And
problem.
then I
just
will
wanted to
make
make
a
sure
short
that-
introduction if
Perfect,
you
perfect.
agree. And
Oh yeah,
then,
please.
yes, but we are waiting maybe a few minutes.
Sure, take your time. Yeah,
Maybe
have a
5
little
minutes,
soda.
not too much.
Yeah. I just want to make sure you guys saw my screen. That's as
Yes.
long as they can see my
We
screen,
can
that's
see you and the screen, so
good.
everything
They can
is
hear
okay.
me. That's perfect. Great.
And I'm seeing that some students and colleagues are writing here in chat that they can see the screen. So I think everything will be okay.
Okay, perfect. That's great. Terrific.
Perfect. Ca să vezi, da. Hai să opresc micul.
Who makes the click needle?
Sorry, I didn't hear you.
Oh, I'm just wondering who owns Click Meeting? Like which company?
No. Now I couldn't hear you very well.
Oh,
The people who are here, the people who participate are some doctors, some colleagues of us from medical schools, and some students and from residency department.
Okay, terrific. And you can hear me okay, right?
Yes, I'm hearing you. So
okay.
I
think it's because both of our microphones are on. That's probably why.
Yes, both are. But after you will start, I will close my microphone to be sure that we'll not have microphone on something.
Perfect. Thanks. I'm gonna turn mine off then.
O să zic să începem în curând, nu? Că cine mai intră, mai intră. Da? Păi eu zic că e ok. Violeta a intrat.
Can you hear me now?
Yes, you are online.
Okay, good. And
okay, thanks.
Sure, thanks. And I'm sharing my screen again just to make sure. Can you see my screen?
Yes.
You see my mouse, right? So
yes, well, we see the screen.
And
yes.
Do you see this?
Yes. Now is the presentation.
Perfect.
Yes.
Perfect.
We can see the presentation.
Perfect.
So,
I'll just leave it there. Great.
Okay, so I think we can start.
Perfect.
Because if you agree.
Yeah, please.
Okay, perfect. So, dear Professor Rashidi, dear colleagues and students, First of all, I would like to address our gratitude to Professor Rashidi for being with us so early in the morning, because I understand that it's very early, and for willing to share with us novelties in the field of artificial intelligence and machine learning. So this is the first presentation as a member of the Council of Doctoral Studies within our university, and we would like to thank you for accepting this position. It's a great honor for us.
Yeah, thank you.
Less than 1 year ago, we had the honor to attend a series of conferences in the field of artificial intelligence and machine learning applied in biomedical field, presented by Professor Rashidi. Today, despite being far from one another, science is unifying us again in this way, unfortunately. For those who did not attend previous conferences, I would like to introduce our guest in just a few words. So Professor Hooman Rashidi is a specialist in pathology, hemato-patology, clinical pathology, and laboratory medicine and bioinformatics. Especially artificial intelligence and machine learning. He's a director of residency program and director of flow cytometry and immunology at UC Davis in USA. Dr. Rashidi's clinical interests include all types, different types of blood disorders, and I'm not mentioning all of them because I'm not in the field and maybe I don't want to be wrong. Yeah. And he also has interest in developing artificial intelligence, machine learning tools for clinical research and educational platforms. As research areas and academic interest, we can mention that Dr. Rashidi is the co-founder, developer, and senior editor of Hematology Outlines, an online atlas used internationally by medical schools and other training programs. Professor Rashidi also developed the educational application HemaQuiz, which includes quizzes in more than 15 categories, quick references, and the game center that allows users to compete with one another. He and his team are working on other projects, including development of artificial intelligence, machine learning platforms applicable for diagnostic, educational, and research use in multiple pathology, subspecialty areas, and other health science disciplines. And I can continue with Professor Rashidi's achievements a long time, but now I'm thinking that it's time to invite you to attend the conference, Automated Machine Learning and the Introduction of MILO, which I think it's a very, very interesting subject, both for medical specialists and computer sciences. So please, Professor Rashidi.
Well, thank you so much for the invite, and thank you for your time, for wanting to listen to this talk. So without further ado, I'm just going to take you through this. This is a project that just recently was finished, and it was a work of several years that we've been working on. So hopefully you'll enjoy seeing what it does and how it's applicable into the future of medicine and just healthcare.
Yeah, thank you.
So, yeah, no problem. I think we have both of our microphones up. I think one of them have to be turned off, right? Because it's echoing.
I switched the microphone.
Yeah, but I think yours is on, so I think it echoes back. That's what I think it does. Do you hear me? Hello? Yeah.
Yes, okay. We can hear you. I'm switching perfect. The microphone.
Got it. Yeah, because it was.
I switch off.
Yeah, no problem. It's just echoing back. I'll just walk through it. Hopefully, it's not echoing on your end. It's you don't hear an echo, right? Do you hear an echo, or is it no echo? Okay, so you already got a sense of my background. You know what I do, so I'm not going to take you through that. You know, this is my background, bioinformatics. This is what I've been doing. I run a big research group within machine learning, and the stuff that I'm going to be showing you right now, they're intellectual property, patented applications of University of California. So that's something that I have to, disclose. So the talk outline will include machine learning overview, machine learning classification, supervised machine learning, what it is, which, and then specifically, as opposed to the previous talk that I gave a year ago, where I showed you image-based and neural network studies that we've done. This one here is not about that. This is about machine learning in non-image platforms. So laboratory values, physical exam findings, that sort of thing. And can you build predictive models that can actually do a great job for you to make decision support? And then finally, I'm going to show you our newest platform, which is called MILO, and show you what an automated machine learning process can do, and hopefully you'll enjoy it. So for those of you who don't know much about machine learning, I think many of you do, but those of you who don't know, machine learning is within artificial intelligence, a platform. The idea there is that you can basically teach the machine to emulate the human. That's what, put it in bluntly. In the way the machine learns, it's got some similarities to the human. So in the human, you learn from touching, feeling. In machines, you learn from data. That's what it comes down to. So some examples of AI and ML in daily life. So if you think that you don't use machine learning, you're probably wrong. But most of you would agree that you are using machine learning in your daily lives. And that could be if you use Siri on your iPhone, or Alexa on Amazon products, or that could be also if you use your email. The email uses a spam filtering, and that's machine learning. So spam versus ham, to tell them apart. So there's machine learning all around us. Facebook, Amazon recommendations, Netflix, all of these things use machine learning. So the main thing is there a difference between machine learning and medical applications? And the answer is absolutely. For sure, there's a big difference between machine learning and medical applications versus non-medical. And the main reason behind that is practice of medicine is a balance between art and science. So experience is the big thing. So you would want to be able to bring that experience of the clinician into an objective way that's measured, that would be able to be learned by the machine moving forward. So in order for you to make sure that you minimize variability between users or experts, you want to have multiple experts involved when they're trying to assign something as being positive or assign something as being negative. So ultimately, you want to be decreasing the chance of inter-observer variability, because if you don't, ultimately this difference in expertise opinion increases that. So that's the most important thing you would want to do, because you want the data to be reproducible when the machine learns it. So there are many approaches in machine learning, but supervised machine learning is by far the most common.
Professor, sorry,
Yes.
but we can hear very well. I don't know why.
Yeah, I think it's because we're echoing.
It's going in and out, so.
Yeah, let's see in your platform if I can, new private chat accept. Let's say yes. Hello. Let me turn off.
Yes. Yes.
Hello. Can you
Yes,
hear me now?
I'm hearing you. Yes.
Oh, much better, because the echo went away. Oh, awesome.
Yes, perfect. But there were some messages on the chat that they can hear, so it's why.
I'm glad they said that. Yeah, because I
Okay,
could hear
so it's
myself.
why I'm interfere.
No. Thank you. So let me actually.
Thank you.
So
Thank
hopefully,
you.
thank you for the heads up. So some examples of AI and ML in daily life. You can hear me now, right? So it's all good. And so Siri versus Alexa, I was telling you, spam filtering. So if you think you're not using machine learning, you are, because spam filtering is the exact reason. By the way, I'm repeating this because you probably didn't hear some of my voices here. And then most of us are using some kind of machine learning in our daily lives. You might not even know about it, but you are. But there's a big difference between machine learning and medical applications versus non-medical applications, because in medical applications, you have experts who have experience that they're bringing along with the science of it. And that experience, so that whole balance between art and science, that actually has value. But different experts may have subtle differences between them. So it's very important for us to actually decrease variability between experts as we build models that are learning from humans. So that's in medicine, that's very prominent. So it's very important to do that because most of the stuff we do in medicine is supervised machine learning. Excuse me. And what is supervised machine learning? Supervised machine learning is a subset of machine learning, as I'm showing here. So machine learning can be split into reinforcement learning, which basically is like you have a robot that learns as it goes. So it's a mix of supervised and unsupervised. And then you have unsupervised learning where you don't need input from the expert and you just learn, the machine learns from patterns that it finds inside without any human intervention. And then supervised is, as the name implies, is you're learning because a human has supervised the initial stuff and has labeled them. So for example, the most common is classification. So let's say you said this group is cancer and this group is not cancer, or this group is, you know, infection and this group is no infection. And then the machine learns from laboratory values that are associated with those targets or other clinical values. And then it basically assigns them as cancer or no cancer, or infection or no infection. And then when you put in a new parameter in there and say, these are the lab values for a new patient, and based on those new patient parameters, it can now predict it. So it learns from the past. And I'm going to concentrate mostly on classification within supervised learning, because that's by far the most common thing that we actually do. But the real world of machine learning, artificial intelligence, is not that easy to deal with. As we've seen in the news, this was from a few years ago where IBM's Watson partnered up with MD Anderson, and the plan was they were going to change the world of how basically to assess cancer therapy and a targeted cancer therapy with their oncology expert advisor. And ultimately, the take-home point was that it didn't work out really well because multiple reasons, but they spend millions of dollars into this. And if you're not ultimately meeting a need, even though you may have a fantastic setup and theoretically it may sound good, you know, the current practice of medicine is not what people outside of medicine think it is. So you'll have to meet a need within medicine. So it's very important to have people within medicine involved who not only are within the field, but also from the field that you're trying to apply the model to eventually, which these were things that potentially we were missing. Ultimately, it's not a very easy project to kind of bring stuff on board just because you have a good platform. So there's some major potential safe applications that you can kind of go after. And the thing that we like to do in my group is we like to go after the lowest hanging fruit. And because that's kind of like the easiest things to go after. So go after things that there's a major need for and they're easier to accept. And the thing that I'm going to show you is our acute kidney injury study. And the acute kidney injury study, which we've had subsequent studies on, I think I touched on it last time when you were at last year's thing. But this was, if you want to build an acute kidney injury model where you want the machine to be able to identify acute kidney injury in a patient. But the current standard for acute kidney injury, and the reason you want the machine to enhance it is because the current standard is this thing called Kidney Disease and Improving Global Outcome, or KDIGO. And KDIGO is based on serial creatinine and urine outputs, so multiple creatinine and urine outputs. And so not surprisingly, because it requires multiple, it's going to take several days for you to get an answer. So that's not good by itself. The second thing is that we were studying it within our Burns population study. And in terms of how well you can predict with KDIGO within Burns population, the sensitivities are not that great. They're in 50s. And actually, the other populations are not that much better. So since then, people have come up with ways to make KDIGO better. And one of them is something that's actually used in Europe. It's called NGAL, and it's neutrophil gelatinous associated lipocalin. And this substance can actually be measured, and this measured substance can predict if somebody may have acute kidney injury or not, and does a better job than KDIGO. But what I mean by a better job, it doesn't, yes, it's not 50% sensitivity. It brings it up into like high 70s or 80s, but it's still not good enough. And within the US, they're planning on clearing it too, because it's such a big improvement over the current approach. But if you notice from this, if you look at, this is with no machine learning right now. If you just group your acute kidney injury, the ones that are positive versus negative, you notice that creatinine measures are all over the place. You notice that urine output is all over the place. BNP for cardiorenal, kind of a little bit better. But NGAL is much better, but you still have NGAL where you have negative acute kidney injury within it. So still not perfect. So can machine learning make this better, where a combination of these may actually prove to be the best approach? And that was our goal. Our goal was to use a combination, and we found out by using a combination of NGAL along with your standard creatinine, urine output, and BNP, that we were able to actually build models that were very predictive and had accuracies and sensitivities of now in the 90s, which was fantastic. And then we had a follow-up study that showed similar thing, where now this was our acute kidney injury study that we did on, we had initially studied our models in Burns patient, and we wanted to see if the same models in Burns patient can be applied to non-Burns trauma patients and other populations. And the interesting thing is that it did a fantastic job. It actually worked really well, as we've published on. And so your traditional different algorithms actually worked out really well within our platform. And ultimately, this is what it showed. So if you can improve with machine learning, so all of these include machine learning. So if you bring in urine output by itself or creatinine by itself, you notice that your ROC-AUC is horrible. You don't have a very good performance. If you combine the two with machine learning, it clearly improves it, but it's still not good enough. But what happens is that when you introduce NGAL and the machine learning both, then now you're getting fantastic models that are doing super, super well. And this one happens to be one with no urine output. So not surprisingly, urine output, you happen to have more variability. So that's probably why. And this is kind of showing you the same things, that, the ones that have no NGAL, they're not doing as great as the ones that have NGAL. So in summary, the acute kidney injury model trained on burn populations are able to predict acute kidney injury in non-burn populations as well, in addition to burn population. And ML enhances the predictive capability of NGAL, and NGAL, when combined with these other markers like creatinine and BNP, can further improve the predictive capability of acute kidney injury when you incorporate machine learning. So not NGAL by itself or NGAL with other markers, but NGAL with other markers and the machine learning. So, but most importantly is that the models that we built, they actually, instead of your traditional approach, which takes, with KDIGO, you can have about 61 hours till you get an answer, we can actually change the time to prediction by a day or two. So you can actually improve the time to diagnosis dramatically by doing our approach, because you're doing it on admission data. So you don't have to get serial creatinine and serial urine outputs. You're doing an admission creatinine, admission urine output, admission BNP, and your admission NGAL. And that's what the power of this approach would be. So what that means is that if you have patients that are traditionally coming in and they require multiple urine outputs and creatinines, and they take several days to get the answer, well, with the incorporating NGAL and machine learning, you can now do it on admission data in about a day or so earlier. So the question can be is that, can this machine learning process that I just showed you, can it be automated? And can you as an investigator, even if you don't have a background in machine learning, can it be automated enough so that you could, or any investigator could use machine learning and do a study as long as they have a great idea? So this way you're not then limited by having machine learning expertise or machine learning expert collaborators, but you basically, you drive your own studies based on your great ideas that you have. And the idea there would be a process where there will be no machine learning expertise needed and no programming or software engineering backgrounds needed. So it would just be easy to do. And our answer to that was MILO. And MILO is, we call it your fully automated machine learning solution, and stands for Machine Intelligence Learning Optimizer. And the reason we did this was, I was just telling you, is a lot of these machine learning platforms are becoming increasingly incorporated or want to get incorporated into the healthcare disciplines and health science research world. And yet, not as many people are involved because they may not have access to a lot of these machine learning platforms. And so the current challenges within machine learning, one is it's intimidating. So the average person who doesn't have a machine learning background, or is not a statistician, or doesn't have a programming expertise, they don't want to go after these studies. And even if they do, and they have, let's say, a collaborator, it will be very difficult for them to talk to each other because they may talk a different language. But so that's one big challenge. The other big challenge, and this one I see all the time, is that most of us have a full-time job. So even if you come up with a fantastic idea, you're going to put it on the shelf and not do anything with it because you have a full-time job, and your idea and doing machine learning in it is going to be time-consuming, and you're not going to pursue it. So if you can find ways that you can do an automated approach that actually can save time as well, that would be fantastic. That one actually by far is my most important in my head. And then finally, as somebody who reviews machine learning, papers all the time, and I've seen fantastic models built and people are publishing on these, and that's terrific. But the part that I find not so great is that when we build these models, they actually stay in literature. They don't get translated into a product. They're more theory. So instead of becoming a theory, you would want to kind of go to the next step and make it live so that you can actually start using it. But if that's challenging by itself, because you typically build these models in Python, and so that's one language, and then now you would want to have another person who has, or another group that has expertise in, let's say, HTML, CSS, JavaScript, and kind of put it in a user interface website platform. And then those connections, a lot of people don't have those resources, along with medical, legal, and other reasons. So there's multiple challenges in terms of wanting to automate the process. But now I want you to imagine a world where you can do artificial intelligence and machine learning studies, and they're as easy as using your website on your laptop or on your iPhone or Android device. It's just super easy. So there'll be no machine learning expertise needed. You don't have to be a statistician. Of course, you need to know some statistics, because the stuff that machine learning is going to give you are statistically based. So I'm not inferring that you should not know anything about statistics. You should know something about statistics, but you don't need to be a professional statistician. So, and then the second thing is that imagine where you don't need any software engineering expertise needed and no programming required, just easy to do. And our solution was MILO, and MILO allows AI ML studies to be accessible to all investigators. So where there'll be no coding, no programming, and no machine learning expertise needed. All the heavy lifting is done by MILO. And so its key highlights are, one is that it expedites the machine learning process and makes it a lot faster. So, and I'll show you the data on that in terms of how much faster. It actually improves the outcome in terms of the machine learning studies that the performance of the machine learning models you get. And I'll show you how it does it, and you'll see it becomes a common sense of why it outperforms the non-automated approaches. And then finally, it's super user-friendly and easy to use. So any investigator can use it. And that's just as important of anything else. So here's what I mean by how much faster it will be able to do it. So these are two separate intellectual properties that we have with University of California, where independently, and they were published. And so our acute kidney injury that I showed you the study on, that took about 4 months to find the best model, going back and forth with different groups and our own group and all that stuff. So MILO was able to do all of that in less than a day, as you can see over here. So 4 months versus less than a day. Our sepsis model, the same thing. It took 3 to 4 months to do, and MILO was able to find the best model in less than a day as well. So you see how powerful that could be. And again, that thing that I just showed you applies to all the other stuff that we've worked on too. And most importantly, MILO is a validated platform. And what I mean by validated platform is that within our studies, and it says 10 IRB studies, but it's actually 11. So we have all of these different studies that are in different parts of medicine that are validated on MILO, and MILO has built best models for. And if you notice, they're not all for just clinical stuff. We also have, be able to build non-clinical predictors that can identify our students who may need help in medical school. So you could find out from student scores and previous performances how well they're going to do in a year and a half, and then intervene and help them to kind of make their lives easier. And that actually, these models are actually live in our medical school now. We're actually using them, and our administrators are using them. But we also have these models, our acute kidney injury module, which is getting incorporated as our best practice alert for our burn surgery colleagues, so that we can do our next trials on them too. So again, different subgroups of healthcare that MILO has built fantastic models for and can be deployed and moved on. Ultimately, this is how MILO works. MILO works like this. It makes no assumptions about your data, zero. And so and the reason for this is because if you brought your data set to a machine learning expert, and so if you brought it to me, I would say, based on my, decades of experience in machine learning, I'm going to basically think the best thing for your data set is a neural network. If you take it to another expert, the other expert may say the best thing for your data set may be, a random forest or gradient boosting machine. Another one may be, traditional, very, parametric statistical approaches. They feel like that's the best thing for it. So they may say logistic regression. And who knows exactly what's the right answer here. And so instead of, a data science expert or data science expert group deciding what's best for your data set, we let your data set decide what's best for it through MILO. So MILO becomes a matchmaker. And it follows industry's cross-industry standard protocol for data mining, which is that modified IBM approach. And actually, ours, MILO actually follows a modified approach of this, which is even stricter because we're dealing with healthcare data. So even pilot studies require 2 data sets for it to be able to pop out something. This is how MILO's architecture works. So everything in the yellow or in the tan, all this tanned area, this is what MILO will do. The only thing the user needs to do is to bring the 2 data sets in. So the user brings the 2 data sets, and ultimately the user brings the 2 data sets, and then the MILO will clean the data, scale the data, finds which features are the best, builds the models, validates the models, and then most importantly, after it builds and validates them on 7 of the most commonly used algorithms, including our neural network and gradient boosting machine, it then secondarily tests it on another data set that's the true prevalence to see how well does it really do. So, and this is the real performance. And then ultimately, if you're happy with the model's performance, then you can actually go deploy it and go live. So we don't stop here. We let you even go live with it. So it's a fully automated and a complete AutoML platform. This is what I mean, like in terms of things that it can do. So our sepsis model took about 3 to 4 months to build. And we were very excited because in burns patients, we found, one model out of all of this. This is one of the largest studies out there in that world with machine learning, about 50,000 models, about 4 months. And we found a fantastic performer. And we were very excited that we found that needle in the haystack for our burn sepsis predictor. And the main question we were asking is that, can MILO do the same thing? And MILO was able to find the same one. So MILO found the same one, but it built, 6 times more models. But the most important thing is that it did it in less than a day. So it found that needle in the haystack. Importantly, because it had built so many models, it actually found 5 more that outperformed the top one, the non-automated approach. And by the way, this thing that I'm showing you, we've seen in all the other studies we've done too. So that's how powerful it is. So, but the way it works is very straightforward, is that it works that way because it has hundreds of thousands of models to evaluate that are optimized models already. So, and then most importantly, it follows best practices within machine learning, as we've published on them and others have published on these. So here's a quick demo of MILO in terms of how it works. So let's imagine you want to predict sepsis and say if a patient has sepsis versus no sepsis. So you're going to do a study on that. So MILO will do everything in the dark, and you as the investigator will bring in these 2 data sets, the balanced data set that you're going to do the training and initial validation on, and then the secondary data set, which is the true prevalence of the disease, which in this case is sepsis, and see how well it's going to do in your study. And so you pick the data set that you're going to be training and initially validating on. And our initial data set was about 500 cases. And these 500 had different values that were collected. So temperature, respiratory rate, heart rate, sodium, potassium, anion gap, MOD score, different values. And then they were assigned to sepsis negative cases, so zeros, and sepsis positive cases, and about 250 of each. So here's MILO's platform. And MILO's platform, you just click the button and upload that CSV that I just showed you. That's an Excel file, CSV file. And then you just basically, if you can attach it into an email, you can attach it into MILO. And you just choose it and it puts it in there, puts a check mark, says that it's uploaded. Now you put in the secondarily, you do the same thing. You put in that secondary data set, which is the true prevalence. In this case, the same features, but a new set of patients. And these are now about 80% of them are negative and 20% of them are positive in 200 and something patients. And then again, the same thing here. You upload it just like another Excel file. So here's your Excel CSV, and then you attach it. And then now you decide which column is your binary classifier. So because we want to try to predict sepsis from no sepsis, you're going to pick sepsis as the final one. The MILO's approach is super simple. It's a 4-step process. You load up the data, like I just showed you how easy it was. You then explore the data in the next step, which I'll show you. And then after that, you then do the brain of it is the training. So that's when you're going to build all the different pipelines, and then it builds the few 100,000 models for you. And then finally, those models are evaluated in the results page. And then you as the user will look at it in the results page. And if you like it, you can then deploy it. It's that simple. And so here's MILO in action. So you now click the button and you upload. And just like I showed you, you put the check mark saying that's good. And then secondary, the same thing. If they don't match, by the way, it will give you a message saying it didn't match. But they match, so it puts green check marks. But here now puts all the columns next to it that pulls it from the Excel sheet. So sepsis is the one. And you say next. And then now you're seeing the 2 data sets. So the data set to the left was the 50-50. That was the 500 cases that was 250 positive, 200 negative. The one to the right was 80% of them were negative, 20% of them were positive. You can see how the data skews in different areas. Now, if you're happy, you can move on. And then this is the part that by default, we recommend you running everything, all these combinations. But you can also customize it. So especially if you're a machine learning expert, you may say, no, I don't want to use the feature selectors. I want to just uncheck them and let Milo build them without the thing, and kind of like you can see the different variations. And for the sake of time, I'm going to uncheck it so it doesn't take that long. So I just say start, and by default, it starts the training and it builds a wheel of pipelines for you. And this wheel of pipeline, a typical machine learning study could be 1 or 10 or maybe 100 pipelines max if you're a big group. In Milo, we build about 2,000 pipelines, and there are individual pipelines that are giving you optimized models. So now you can see the neural network, naive Bayes, logistic regression, each one. Obviously, this is going to take hours, so I'm not going to take you there. So a little while later, after several hours, that wheel will get to close to 100%. And once it's close to 100%, it then now will put you into the results page. And in the results page, you can see the top model, which is our average of sensitivity specificity pop up. But you can change that. You may want a model that's the best ROC-AUC, or a model that's the best F1 value, or the one that's best accuracy or sensitivity, whatever you want. And you can decide. And the graphs correlate with the model that's in that live table. And it's very transparent. So you can see exactly what you ran, how many models you've ran. So this one is 129,000 models built, tells you what's built there, 500 patients, 250 each, 200 patients, and 10K cross-validation was done. Now, let's say you're happy with this, and let's say you found that this is a good model you want to deploy because it had 100% sensitivity and 85% specificity, and you're really happy about it, but you don't know exactly, it says that it did it with 50% of the features. So, but now you want to know exactly what 50% those were in that Excel file. Well, Milo is very transparent. So you can now just go to that, instead of looking at this table, because we don't have enough room, you can download that entire table and a lot more data into your desktop, and then pull it up as an Excel file and just look at it in more detail. So if you want to do the statistics again, because we give you the true positive, true negative, false positive, false negative, you can redo the entire statistics. If you want to rebuild the models in Jupyter Notebook or other things, we even give you the parameters. You can rebuild them. We validated them with those parameters. But in this case here, you wanted to see what those features were, right? So you can just go to the column where it says features selected, that middle column, and then expand that column and see what those features were. And so you can now compare it to all the features. So if you notice the 50% features in that top model was respiratory rate, temperature, white blood cell, versus all of the features, which is further down. So it gives you a lot more info, and you can actually do your study a lot clearer than not. And now if you're happy with this model, you can now go live by pressing the green button here. So you click the green button, and now this is a live model on a web app that you can actually start testing, either single test or batch test. It could also be as a PMML, downloaded in LIS, and where it uploads automatically from your computer system. But now I'm going to put in some values for a typical sepsis patient, because this is a good model, so it should be able to identify a sepsis patient. So you put in some values that you think somebody with sepsis should have, and then I put these in, and once I put them in and it has all the values, it says you can press predict, and then the model can quickly predict for you. It says it's a positive patient, probability of 62%, and then you as a clinician can decide if that's really, what you're going to do next with that. But you can also do a batch study. You don't have to do it all. So you can actually build that model as you don't have to retrain it every time. So you can actually fix it, put it on your homepage, and now it's a best KNN sepsis that you just built as a website. And then that website, now it's ready to test the models in the future without having to do training anymore. And let's say you wanted to do a batch test on the secondary data set and see which ones it got wrong, which ones it didn't get wrong. Within seconds, it actually gives you the answer. You can now download that CSV Excel file and see exactly what the prediction was. The last two columns are the prediction versus probability right there. And so you can see exactly which ones it got right. So, 80% of them were negative, but some of them are erroneously called positive. So you can actually kind of see exactly why they were called positive erroneously. So you get to see a lot more granularity in there. So you see the power of all of this transparency that comes within your model. Ultimately, in summary, it's super easy to use. It doesn't require any machine learning expertise. You should know stuff about statistics so you can evaluate the models and do the proper studies. But no programming and software engineering is needed because it's all web-based. And it's basically your machine learning and software engineering expert team in a package, in a software package. It follows machine learning best practices, most importantly. It does it much, much faster than the non-automated traditional approach. And most importantly, it's a validated platform within the niche that we're in. And these are our collaborators who have helped, and there's additional ones that I haven't listed just because of space. And I like to thank, and I thank you for your attention. So I hope you enjoyed it, and I'm happy to take questions.
Thank you very much for the interesting presentation. I think that everyone is convinced now that MILO is very fused in medicine and probably in other fields, but now we have an example for medicine. And I will let now the attendants to put some questions or to have some discussions. So please, those who want to ask something, please raise your virtual hand, and you will, I think you can have the microphone and ask, or you can write the question if it's not too long inside the chat. So until they will decide, I see that we have a question here.
Yeah.
Are there any MILO for dentistry?
Yeah, you can use it for anything. It's not just dentistry. I mean, the stuff that I showed you is MILO is just a tool. So this tool can be used for anything. So any idea that you have that you would want a machine to build a model for, MILO builds that model, but automatically. You just have to bring the great idea in. That's all you got to do. And so that's the big thing, is that it encourages more investigators from different disciplines of health to basically come on and do stuff, you know. And if you notice, the stuff that I showed you, they were building models not only from cardiology, from, you know, transplant surgery, transfusion medicine, pathology, laboratory medicine, burn surgery, but also from education, like curriculum, in terms of how well the students are doing. So it has relatively agnostic features to it too. So yes, this could apply for any idea you have that you could basically test out for.
Thank you for your answer. I see another question. Can MILO be used to detect a possible gene that can be mutated in the future?
Yeah. So it can be, but I'm not suggesting, because in like a lot of genetic studies, we use, you know, you pull out thousands of gene candidates, and then you have to decide which ones are the best ones to pursue, or the highest yield to pursue. So I'm not suggesting that you should start off with MILO on that. So for something like that, if you have thousands of genes and you want to narrow it down, classically, what I recommend people to do is kind of do, you know, some kind of a dimensionality reduction, like a principal component analysis or something like that, where they can, you know, they can find out which subset of genes or which genes happen to be the ones to kind of like target. Instead of, let's say, 10,000 of them, maybe they can narrow it down to 1,000 or 500, that sort of thing. And then once you have it narrowed down to a manageable thing, then you can feed it into a platform like MILO.
Okay, thank you very much for your answer. Another question. A quantum computer will work better for this MILO. I have it in my garage.
The what? Say it again.
A quantum computer will work better for this MILO. I have it in my garage.
Oh, okay, yeah. I mean, so to be fair, yeah, and definitely MILO's platform. So I'm not going into details on hardware in terms of how we compute. So MILO actually uses by design, it's a CPU based approach, but CPU or GPU, whatever you use for you know, machine learning, the future is going to be quantum computing. So you'll be able to use quantum computing to make it do so much faster. But yes, we will be looking at those, and we have kind of similar studies here where we're testing out some of these platforms.
very much again. So Professor Shebesh, I think he wants to put a question.
Yeah, say
So
hello to
I
Professor Shebesh.
hope, Alex, please give the microphone to Professor Shebesh if it's possible. So, someone is typing.
Oh, that's okay.
So, because only two of us, we have microphones now.
Oh, no problem. No problem.
That's why I'm asking the administrator of the meeting to give the microphone if it's possible.
Sure. No rush.
One of our colleagues. Until then, we have another question.
Yeah.
Is MILO explicitly supervised machine learning, and is there potential for other machine learning methods with MILO?
Yeah, so that's a good question. So I have to say MILO is, both supervised and unsupervised. So if you noticed from the infrastructure, it does unsupervised platforms first, where it finds the best features without a human, and then it does supervised learning. Hi, Dr. Kodarachi, how are you?
Yes, I just wanted to write you.
Yeah.
Okay.
Yeah, so that's true. It will do both unsupervised and supervised, and then that basically gets the machine to learn from each other. So the unsupervised stuff that it's learned gets fed into the supervised platforms, and then they basically build different variations of models. Some of them that have not been picked out any unsupervised platform, so all the features, and then some of them that have picked out a subset of the features and basically done supervised platform. So that's definitely done. We already have it in. That's how MILO works, actually. Now, in terms of future, right now MILO is just for binary classification of non-image. So, and the reason for that was because 90% of the people who brought up projects in terms of they wanted my lab to do, they wanted projects that were non-image binary classification, like acute kidney injury or sepsis prediction or delayed graft function prediction, all of these laboratory physical exam. So they were numerically based kind of functions. In the future, we will be doing natural language processing functions within it, and then after that, we may also tap into image-based analysis and whatnot. From a transparency standpoint, I have to say that MILO actually it's getting licensed to different companies, and it's actually it just finished its license with the first company yesterday. So it's going to be used in different segments of industry and segments of healthcare, in addition to academia and research.
Okay, thank you very much for your answer. I think,
Thanks.
Professor Shebesh, you have the microphone, so you can ask questions if you wish to.
Yes. Do you hear me? Hello?
Yes.
We are hearing you.
Hello.
Good to hear you again.
In the context of machine learning,
Yeah.
to have a creative research question in an application field means, according to me, to identify which are the independent and which are the dependent variables. What other idea can you have?
That's a very good point.
I mean, if you don't, if you are not so much interested in the part of programming or in the part of model adjustment and the model building, or as you said, the person who is applying the model should not necessarily bring these skills with him.
Exactly.
Then what else can it be to have in the context, of course, in the context of machine learning? What else can it be?
Yeah, so that's a great question. So the part that I'm not suggesting that MILO will replace me or you. What I'm suggesting is, I'm actually saying it because we have so many data sets now to show it, is that it allows a lot more investigators who usually had no access to machine learning to be able to do more machine learning. But that being said, when MILO can speed up the work that you do and I do. And that means that if we basically want to put in more concentration and want to optimize, instead of concentrating on a neural network, we let it automatically find the best models initially. And then we go back to our lab and say, MILO found the support vector machine and the neural network to be the best 2 out of these 7. So we can then concentrate on those and optimize those to even be better than what MILO has put out. So I think in the machine learning world, people will take advantage of it too, because it optimizes the process, because it really does the work of 50 to 100 data scientists. And so, but at the same time, I think that once the user becomes better and better with it and understands the fundamentals behind it, then they can change the data around and see what kind of outputs they get. So they may actually remove some of the features and find out that some of the independent variables, that MILO was able to pull out. If they actually pulled them out earlier, they may even enhance MILO's approach even faster. So things that, we typically try to calculate, MILO will maybe be able to empirically give us kind of like a head start, and then we basically enhance it further. But that's a very good point.
I have another question. I have done some work along the lines of combining models several years before, but not in the context of medicine. And one thing which I was observing is that if you have thousands of models, which we were generating once upon a time at the University of Bremen in Germany, we found out that some or quite many of the models, although they looked very differently, they had a very similar behavior. You see, the form and function. This is a problem, especially with neural networks.
No, you're 100% correct. Like if you rebuild the same neural network with the same hyperparameters, you'll get a different result, as you know. So you're 100% right, and that's true of course of a random forest as well too. But the reason, obviously, we know that happens because those, as you mentioned, those are ensemble models. Now, the nice thing within MILO, which I'm not showing here, is we also have developed another version of MILO, which is called MILO Pro. And MILO Pro basically does exactly what you said, where the investigator does the machine learning studies, and let's say they're a machine learning expert, and they now can actually use MILO Pro to select which models they want to combine together and make it as a new ensemble. And so,
that's nice.
We have that in there. Yes.
And the last one, maybe, I put this question before when you were visiting Arad. What about transfer learning and applications in medicine?
So to be fair,
you have some models which are already trained on other similar problems, and you may use them.
So that's definitely, we do that, but not in MILO. So transfer learning is something we use regularly within my other subgroup of neural network studies, where we do it with image analysis. And the reason for that, as you know, the gold standard for image analysis studies is neural networks. So since the neural networks, building them from scratch takes forever, as Andrew Ng and others have said, the transfer learning can kind of give you very similar and sometimes even better results, and in a much faster fashion when you're doing those studies. So within the image-based studies, we definitely do transfer learning. Within the non-image, now I can see in the future where there is a lot of these things have already been done, and neural networks that have been optimized or other algorithms that have been optimized, that then you can learn from those optimized ones to do transfer learning on, let's say, non-image stuff like what we're doing. But at this point in time, there is no data as such. It's not like the image stuff that people are currently using, because in medicine, like we use the transfer learning for when somebody's trained on dogs and cats and other things, and there's a lot of commonalities in image architecture, especially in the first few layers of the neurons, compared to what we have, let's say, a histologic view. And so for those, we basically do transfer learning to save us a lot of time, and it enhances the stuff, as you saw from my last year's talk. But for these, because there are laboratory values and we don't have the outside industries, they haven't really built neural networks or optimized models yet that basically we could use to do transfer learning on. You have to do them from scratch. And this was a way for more people to be able to do these, so that what you just suggested, that maybe in the future, these can be combined and better models built, and maybe in further future, people can do transfer learning off of that as well too. But we don't do that in MILO.
Thank you very much. Very informative. And
Thanks
see
again.
you. Maybe we'll meet again. Thank you.
Yeah,
Thank
I
you.
hope so.
We hope we need to continue this discussion. Please, I would let
I just want to thank you very much and to salute you.
Thank you so much.
I'm very happy that this beautiful project of ours had such a nice continuation, and I really want to thank you for all your implication and dedication, and
thank you. Thanks so much.
I'm very happy to see you healthy, and I wish you and your wife all the best.
Thank you so much. You too. I hope you guys are all doing well too. And this is a crazy time that we're living in with COVID. And but I can see it will be behind us in a couple of years. I don't think I mean, we'll get over it. It's just time. So it makes us stronger. So that's the best thing. So.
You have to make a prediction model.
That's right. I have to make a prediction of how much stronger we'll be. Yeah, that's right. Actually, kidding aside, MILO is now it's actually the predictive analytics platform for one of the WHO sites for COVID for Pakistan, and it's also used in the University of California for our own ICU predictors. And we also have a multi-center kind of like a multiplex study with cytokine stuff, and so it's being used in a lot of other platforms too, which I'm not mentioning. But yeah, we're excited if we can help with the process and kind of move it forward. But I don't think it's any one person who can kind of do it. It's going to be a global effort that basically can bring this to an end, really.
How about the new academic year? What do you predict? It will be online? Or
I think this coming, I mean, personally, I think until there's a vaccine, and because let's face it, with us bringing it down, we're not probably getting I'm not even sure how much herd immunity is doing, but let's say hypothetically, if it works, reality is, in order for us to actually have long-term immunity, people have to come up with these vaccines that are going to help the world. And I'm very hopeful that that's going to happen. I think the world is coming together and they're going to make it work. I think the challenge is going to be to actually delivery of all of this. That's going to be the biggest challenge, because I think that will take time. And I'm just hopeful that it will, that it will basically make it better as the academic year goes on. But I don't think it's going to be like magic where it's going to go away, as you know. I mean, I think we need kind of a final solution for it.
Okay. Thank you very much.
Thanks so much. Thanks again for the invite. I hope you guys all enjoyed it. Thank you.
Yes, we did. Thank you very much.
Take care. Bye-bye.
Thank you all of you for attending the conference, and we hope that we'll meet again in other conferences and maybe in future face-to-face.
Oh,
thank
yeah, I'm looking forward to it. Yeah.
Thank you for all of you.
Thanks so much.
Thank you. Thank you. Bye-bye, and all the best. Thank you very much.
Thanks.
Thank you, Antonella, and thank you all for being here.
Thanks, guys. See you, Dariana. Thanks. Bye-bye.
Thank you. Thank you.
Thanks.